Hi everyone, in this video we'll be exploring tests for convergence and divergence of type 1 improper integrals. That means we're going to talk about their behavior. First of all, let me tell you why we need tests. We need tests because there are some improper integrals, like this one. Okay, like this one. There are integrals that you cannot evaluate. So you cannot use the limit definition of the improper integral to find out if this is convergent or divergent. That's why we need tests. Okay, the tests will only tell us the behavior. It will tell us if it is convergent or divergent. But in the case of convergence, it's not going to tell the answer. Okay, in order to find the answer, you still have to evaluate the improper integral. We have two tests. One of them is direct comparison test. The other one is limit comparison test. Okay, what I'm going to do is, first I'm going to take 3 examples and use direct comparison test. Then I'm going to take other 3 examples and use limit comparison test. And after that, it's up to you to decide which test to use with which improper integral. Now, let's go over the direct comparison test. The direct comparison test says that if those 2 functions are continuous on this interval and, okay, this is important, both of the integrands are positive. If both of them are not positive, this is not going to work. And this is inequality between these 2 integrands. That means f of x is smaller than g of x. Okay? The direct comparison test says that if the improper integral with this integral, okay, the improper integral with this integral converges only if this improper integral converges. Okay? The next one says the improper integral with this integrand diverges only if this improper integral diverges. So, if this improper integral is convergent, this will also converge. If this improper integral with this integrand diverges, this one will also diverge. It's like smaller than convergence, converges, greater than divergence, diverges. Now, let's get to our examples. Let's start with the first one, okay? I am going to use the direct comparison test. That means I'm going to start with the given integrand. Okay, now I have 2 options. Either I'm going to write something bigger or I'm going to write something smaller. Okay, I'm going to write a g of x here. Okay, this I'm going to decide. So how do I do the decision? That's the problem. Well, I don't have much to think about. I have the p integral that I know it converges if p is greater than 1, and I have it diverges if p is between 0 and 1, and I have e to the power x, which is a divergent improper integral because of the limit definition. The limit doesn't exist. And also I have e to the power minus x, which I know it converges. So overall, I have these 3 options to put on the right-hand side, either something bigger or smaller. So on this right-hand side, I don't know yet the direction of the inequality. Either I'm going to put a p integral, either I'm going to put this, or I'm going to put this, provided that I know the comparison. Okay, what do I know about sine square? I know that sine square is between 0 and 1. So if I put 1 in the numerator, that means I put something bigger in the numerator and I don't change the denominator. So this is the direction of the inequality. This is 1 over x squared is greater than sine square over x squared. Now I have to see and go back. I know that if this is convergent, this converges. If this is divergent, the test is not going to work. Now let's see. From 1 to infinity, 1 over x squared dx. I take exactly the same limits of integration. This is a p integral. P is greater than 1. It's equal to 2. It's greater than 1. Converges. Okay. Why? Because I know it. We have proved it in the previous video. So, therefore, since sine squared x over x squared, 1 over x squared, this is the inequality, by direct comparison test, this improper integral also converges. Let's consider the second example, from 1 to infinity, e to the power minus x squared dx. Now, let's try to find out the answer by using the limit definition. Okay, limit b tends to infinity from 1 to b, e to the power minus x squared. This, we cannot evaluate this integral. Okay, e to the power minus x squared. So, we cannot find the answer by using the limit definition. So that's why we are going to use the direct comparison test. That means we're going to write something smaller or something bigger. Okay, we are going to decide now. Okay, we are trying to decide. Okay, how do we decide? We know that for this we have one of these options. Either I can compare it with a p integral, or I can compare it with this integral, or I can compare it with this integral, okay? There's nothing like x to the power p like the previous one, so it's for sure I'm going to compare either with this or with this, okay? So since x is between 1 and infinity, x is less than x squared, minus x is greater than minus x squared, so e to the power minus x is greater than e to the power minus x squared. So that means here I'm going to write e to the power minus x. So what do I know? I go back to my direct comparison test, okay? If this improper integral converges, this will also converge. If this diverges, the test is not going to work, okay? If this improper integral diverges, this will also diverge. If this converges, we don't know what will happen to this. The test is not going to work. So, what do I know? From 1 to infinity, e to the power minus x converges. Why? It's here why, because there is an answer to the limit, okay? And this is smaller, so that means by direct comparison test, from 1 to infinity, e to the power minus x squared dx also converges. But to which value it converges, it's an unknown for us, okay? We only know that it is a convergent improper integral. Let us consider the last example that we're going to use direct comparison test. Okay, I have 1 over sine squared plus x. Okay, I know that if I get rid of this, I'm going to end up with a p integral. Okay, so there are two ways of getting rid of sine squared. Either you can write its maximum value or its minimum value. If you write its minimum value, then the denominator decreases, the quotient increases. If you write the maximum value, the denominator increases, so the quotient becomes smaller. Okay, let's take this one. 1 over x. X, p is 1, P is 1, it diverges. Okay? If this diverges, we don't know, the test is not going to work. The test only works if this is convergent, this is convergent. So here the test doesn't work. Okay? Let's move to the second one. Okay? I have written down 1 over 1 plus x. It's not a P integral. Okay? I have 1 here. So I continue to write something even smaller. So instead of 1, I write x. X is from 1 to 2. So x is a greater value than 1, so it gets smaller. So I have 1 over 2x. If this is divergent, this will diverge. If this is convergent, it's not going to work. Now let's see. From 2 to infinity, I take exactly the same limits of integration. Okay, then I take 1 over 2 out. P is 1, it's divergent, which means this is also divergent because you're only multiplying with 1 over 2. So if this is divergent, by direct comparison test from 2 to infinity, 1 over sine squared x plus x dx also diverges. The next theorem that we're going to talk about is limit comparison test. Okay, we have to be very careful that both of them are has to be positive. If not, the test is not going to work. So we just take the limit of their ratio. Okay, and we have 3 options because they are always positive. Minus infinity is not an option. If this is a number, positive number not equal to 0, then they both converge, both diverge. That means they have the same behavior. If this is 0, this limit is 0, I have an extra condition. Okay, if this limit is 0 and the one in the denominator converges, the one in the numerator also converges. If this limit is 0 and this is divergent, it doesn't work. If this limit is infinity, then I have an extra condition. And the one in the denominator is divergent, the one in the numerator also diverges. If this is infinity and this is convergent, the test is not going to work. It's like 0 is hand in hand with convergence, infinity is hand in hand with divergence. If you have a number, then you are very lucky because they have the same behavior. So our ultimate goal is always to have a number for the limit, because if you have 0 or infinity, you have an extra condition. Now, let's get to work. X plus 3, x minus 1, x squared plus 1, dx from 2 to infinity. I'm going to use the limit comparison test. That means I'm going to take the limit as x tends to infinity. I'm going to put the given integrand in the numerator and decide for something for the denominator. I have to come up with something. The something that I come up for the denominator, I should already know from the start if it is convergent or divergent. What do I know? I know what the P integral is, convergent or divergent, and I know e to the power x and e to the power minus x. So my choice is for the P integral, I'm not deciding which P to put at first. I'm just trying to see what is going to happen. X minus 1, x squared plus 1. So I have x to the power P here, So I have polynomial over polynomial, What do I want my answer to be? I want the answer to be a number, because then I don't have an extra condition, The polynomial is of 3rd degree in the denominator, so I'm going to go for 2, okay? Because if I put 2 for p, okay, what do I know for 1 over x squared dx? P is equal to 2, greater than 1, converges. If x to the power 2, what is this limit? It's the ratio of the leading coefficient, which is 1 over 1, so the answer is 1, which means by limit comparison test, both converge or both diverge. Okay? What do I have? I have a convergent one. So because the one that I have put in the denominator is convergent, the given improper integral is also convergent. Now let's consider this second example. We're going to use the limit comparison test, so that's why I write the given integrand in the numerator. I'm going to show you how we do trial and error, okay? Now, my first trial is to put 1, okay? When I put 1, I already know that the improper integral that I have put in the denominator is divergent. Why? P is equal to 1. So, if it is divergent, if the answer is infinity, it's going to work. If the answer is a number, it's going to work. If the answer is 0, it's not going to work. The test is not going to work. So I put 1 here. Okay, I take this. Okay, they have the same power, so the limit is 1, and the limit of inverse sine 0 is 0. So the answer is 0. The one in the denominator is divergent. The test doesn't work. So I go to my second option. Let's write 1 over x squared. So when you choose 1 over x squared from 1 to infinity, p is equal to 2, greater than 1, it converges. So if the answer is 0, it's going to work. If the answer is a number, the test is going to work. If the answer is infinity, because the one in the denominator is not divergent, it's not going to work. Now let's see what this limit is. Okay, 1 over x squared, this becomes x squared. Then I split x squared as 1 over x and x. Okay, it's x squared, still x squared. Why do I do this split? Because this limit is 1, this limit is also 1. So the answer to this limit is 1. Why? The limit as x goes to infinity, inverse sine 1 over x over 1 over x. If inverse sine 1 over x is t, I have the limit as t goes to 0, t over sine t, which is equal to 1. I do this substitution in order to find the answer to this limit. So that's the best answer because we have a number. That means by limit comparison test, both converge or both diverge. Okay, since from 1 to infinity 1 over x squared dx converges. Why? Because p is greater than 1. From 1 to infinity, inverse sine 1 over x over 1 plus x squared dx also converges. So this is how we do trial and error. I hope you found this video helpful. In this video, we have talked about tests for convergence and divergence of type 1 improper integral. We have explored limit comparison and direct comparison tests, and we have taken a few examples to see how we use these tests to find the behavior of first type improper integrals. This is just an overview of the test. If you want to understand the topic in depth, you have to do some more reading. Bye everyone.